Welcome to Who's in STEM. I'm Ken Ono, your host, and the STEM advisor to the provost and the Marvin Rosenblum Professor of Mathematics at UVA. Our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. The other day, I made a list of the exciting and significant UVA STEM discoveries, inventions, and projects that we've covered on this podcast. And if you list them alphabetically like I did, the A's alone are quite amazing. So you get that A's alone are amazing, a bunch of A's. But more seriously, we've talked about AI, artificial intelligence. We've talked about the artificial pancreas, that A. We've talked about autonomous vehicles. And for another A, we've talked about the very serious, crippling disease, Alzheimer's. Going beyond the A's, the list goes on and includes lots of exciting things. The new Manning Biotechnology Institute, the Brain Institute, data science, the Environmental Institute, the Link Lab. Last week we talked about national security and so on. STEM is really happening and happening big at the University of Virginia. It's clear that we're much more than Thomas Jefferson's University, the University of Secret Societies, and the University with the Rotunda. Now, in Who's in STEM, we also feature and talk about the basic sciences. And as a mathematician, I have to assure you that the basic sciences come before everything else that I've just described above. We've had episodes on astronomy, biology, mathematics, physics, and statistics. The basic sciences, they're fundamental and essential to our foundational understanding of nature and just basically how the world works. And along these lines, today it's my great pleasure to talk about chemistry. When I was 10, my parents got me a kid's chemistry set that came in a large box with a handle, although I don't ever remember taking it anywhere. You could see the little bottles of chemicals and glassware through the clear plastic. It was so cool. Ever the science nerd, I'd go to my basement, put on the goggles, and perform experiments with my dog Igor by my side. What kind of experiments? Well, the grosser, the better. Here are some of my favorites. The stink bomb, based on the production of hydrogen sulfide from odorless sulfur. The volcanic lava flow, made by combining baking soda with vinegar. And, well, I also love the invisible ink. This was a simple experiment, just made with a lemon juice concoction. You see, messages emerged when the lemon juice ink was exposed to heat, teaching us about the power of oxidation. The oxidation and the heat turns the ink brown. I also love the mesmerizing underwater fireworks that formed in a clear glass beaker, all due to gravity. What did that experiment teach us? It was nothing more than, well, a few eyedroppers and a bunch of different colored fluids that came with different densities. Now, make no mistake, the stuff of modern-day chemistry is nothing like the stuff of my basement experiments. And chemistry is thriving at the University of Virginia, and we want to talk about it today. And it's a pleasure to be joined by Jill Venton, the Thomas Jefferson Professor of Chemistry and the current chair of UVA's Chemistry Department. Jill, welcome to Who's in STEM.
Thanks, Ken. It's great to be here.
So, Jill, so much to talk about. Chemicals are everywhere around us. Chemistry is obviously much more than my juvenile fascination with stink bombs and invisible ink. Now, as a college student, I took some chemistry classes. They weren't my best classes. The courses that I remember taking went by the names like OChem, PChem, Chem 101. That was the very first one. And generally, these classes were offered at 8 o'clock. Here at UVA, as department chair, what's chemistry?
Thanks, Ken. So chemistry is really the study of molecules that make up all of matter, from air to space to the human body. And so chemists really study those tiny building blocks of life. And so much of the matter of living things is made up of molecules that have carbon as their center. And so chemists call the study of anything with carbon organic chemistry. We tend to call it organic here instead of OChem. But that's one of the main specialties of chemistry. Now, if you study basically any element on the periodic table besides carbon, we call that inorganic chemistry. Inorganic and organic chemists together often are called synthetic chemists. That's because they often make new molecules. So they're interested in the science of making molecules. But not all chemists make molecules. Some of them just study molecules. So there's other areas of chemistry that are interested in studying molecules. For instance, physical chemists or p-chemists study the physical properties of molecules, such as maybe how a molecule interacts with light. And then many of them use those studies to model and predict different chemical properties or behaviors. Analytical chemists, that's what I am, do a lot of analysis of samples to understand what chemicals are present in them. So examples of analytical chemistry include things like forensics, to look at drugs in a sample, or measuring an environmental sample to see what contaminants are in it. And then lastly, there's biochemists. They combine biology and chemistry to understand really the molecules that make up everyday living systems, things like proteins and DNA.
Jill, thanks for that very quick lesson. Now, at UVA, you chair the Department of Chemistry, and you just told about many different disciplines within chemistry. Tell us about the makeup of the department and how the faculty you have represent these various fields.
All right, so the mission of our chemistry department at University of Virginia is to perform cutting-edge chemical research while training the next generation of chemical scientists. And so we're a large department. We have about 30 tenure-track faculty. And so these are faculty that both teach and then run research groups. And then we also have about 6 teaching-track faculty that primarily concentrate on teaching chemistry. And so every year we have about 100 students graduate with a bachelor's degree in chemistry, and another 8 to 10 with a master's degree, and then about 15 to 20 that get a PhD or a doctoral degree in chemistry. Also, a fun fact, each year we have about 10,000 student enrollments in chemistry courses. So those are separate. Some students take more than one course, but that just shows you how large a department we are.
Did you say you have 10,000 chemistry students, 10,000 butts in seats in your chemistry classes?
Yes, that's true. We have over 10,000 student enrollments or butts in seat in chemistry classes. Wow. We are a large operation because chemistry really touches so many other disciplines. So, for instance, many science and engineering majors will require a chemistry course in theirs. And, of course, we all know that many of the pre-med students as well enjoy taking a lot of our chemistry classes. And so we're able to do a lot of good teaching, but also research. Our department brings in approximately $12 to $14 million a year in external funding for chemistry research, and both undergraduate and graduate students participate in that research mission.
So, Jill, that's amazing. I remember when I was taking chemistry in college, I thought of every professor as the leader of kind of a significant enterprise. Are you saying that we have 30 chemistry tenure track and tenured faculty members? That mean we have roughly 30 different research labs here at UVA?
Yes, that's what that means. And each lab works on a slightly different topic, but it's really fascinating to think that we have so many different labs and so many experiences that our students can have to really learn about chemical research.
Well, that's really quite an operation. Now, among these 30 professors, and I'm sure they're all doing fascinating things, and our time is limited, but I do think it's important if you could share with us some examples. Can you show and tell us about some of the exciting research that's going on in your department?
UVA chemistry has many unique specialties that I'd like to highlight. So one of these specialties is astrochemistry, which is studying the chemistry of space and how stars form.
So tell us about that. I would have thought that space largely is a vacuum. So that we have faculty studying astrochemistry is fascinating. Must be a fairly new field. I didn't learn about it certainly in high school. Tell us about it.
Yeah, so astrochemistry takes advantage of some of the latest and greatest telescopes that have been designed to really measure spectroscopic, or how molecules interact with light, signals in the faraway space. And so people like Professor Rob Garrod and Professor Eric Herbst and then Professor Ilse Cleaves, who has a dual appointment between astronomy and chemistry, they look at these molecules, look at the spectra that they get from telescopes, and then try to recreate sometimes some of those reactions in a chemistry lab to understand how molecules are formed in space. So another specialty that's really been growing at University of Virginia is inorganic chemistry and catalysis. So clean energy applications such as solar energy require a catalyst. And so that catalyst's job is to be a helper to turn something like sunlight into a molecule that we can use for energy. And so our department has a lot of expertise now in developing new catalysts and nanoparticles to be able to transform energy applications. In fact, last year we even had the Secretary of Energy, Jennifer Granholm, come and visit our department because of the well-regarded programs we have and the fact that we have been awarded several Department of Energy center grants to study catalysis.
Well, that's really interesting. So I think all of us understand the need for clean sources of energy. That's a given. The process, to me, sounds a little bit like the process that one goes through when trying to find new drugs, right? In your search for new catalysts, you need to find the chemicals or the molecules or the compounds that work, are inexpensive, cost-effective, do not do damage when implemented, so on and so forth. So I'm excited to see that we've got multiple labs presumably working on all of these different questions.
Yeah, so the problems that you listed, Ken, are absolutely correct. A lot of our focus now is on making catalysts from more earth-abundant metals, not rare metals that are hard to find and very expensive, but instead iron or things like that that are very abundant, and trying to make better catalysts from that. And that's going to be more eco-friendly and also more cost-productive. Right. So a final area we have a lot of expertise in the chemistry department is biomedical applications of chemistry. So we have several groups of those organic chemists who make drugs for things like cancer applications. So we also have groups that develop different molecules that emit light. We call that fluorescence. And they use these fluorescent molecules then to track different proteins or different membranes in the body and in tissue to really understand the basics of biochemistry. And we even have some professors here who have done analytical experiments to develop devices, such as Professor Landers, who developed some COVID testing, or Professor Pompano. She was able to develop a device that can keep some thin pieces of tissue alive and then really study the molecular interactions that are happening in a piece of tissue.
Wow. Among these chemists, do some of them have joint appointments with our School of Medicine, or some of these research projects shared projects with our medical professors?
Yes, absolutely. Many of our faculty have a joint or a courtesy appointment in the School of Medicine, and also our graduate faculty in the Biomedical Sciences program. One of the things I love about UVA is that the barriers are really low to collaborate. And having the medical school on grounds in the same location as the chemistry department means that it's very easy just to walk down the street and be able to work with different biomedical labs.
So, Jill, the fluorescence is fascinating. I only think of two things, really. First of all, how to spell fluorescent. It was a spelling word in second grade, a hard one. But I also think about the flickering old fluorescent lights. And I think about like a fluorescent bay that I recently visited, where the organisms have this ability to biofluoresce. So tell us about the work and the applications of fluorescence.
So one of the examples of fluorescence that I think about in nature is the firefly. And so it turns out the firefly has a chemical reaction that happens to make it light up. And we call that enzyme that does that firefly luciferase. Well, it turns out when I talk about making assays to turn on some fluorescence in the body to look at a protein, that we often are borrowing from nature. And so in this case, we can borrow the enzyme, like firefly luciferase, and then use it to make a luciferase then reaction that might be able to track a different type of enzyme in the body. And we talked before a little bit about catalysis and that inorganic people were using elements like iron to make catalysts. Well, it turns out enzymes are the body's catalysts. They are biomolecules, proteins that change one molecule to another. And so we borrow from nature, like the luciferase, to understand other types of enzymes in the body.
That reminds me of one of our earlier episodes with former UVA Vice President of Research, Mel Ramasubramanian. And I asked him what he was most well known for in his research. And he had a very similar story where instead of studying the firefly, he studied the mosquito. And it was on a trip to some faraway camp, I believe it was in northern Wisconsin, where he got bit by a mosquito and he had a flash of insight. And he thought that by studying the mosquito, he could improve vaccine needles. And that turned out to be one of his research accomplishments that he's most well known for. So I love it when we learn from nature. We want to understand nature, and of course that requires first trying to study and then, in I guess some cases, emulate what nature does so well. Now, Jill, I know as chair, you've described a number of the research projects and the work of the faculty in your department as rather humble. I've got to talk about you, too. Tell us about your research. I want to know, what are you known for? Obviously, it's significant. You're the Thomas Jefferson Professor of Chemistry. It's an honor that recognizes your scholarship. Tell us about it.
So my area of research is really neurochemistry. So neurochemistry, again, is the study of chemicals in the brain. My expertise is designing tiny little electrochemical sensors that allow us to peer into the brain and really understand neurochemistry. So part of my lab develops these tiny little sensors, and we use really cool new technology like nano 3D printing. And so we can make electrodes that are only a few hundred nanometers wide. So that's like 1/100th the size of a human hair. We take these electrodes and we use them to study chemical signaling in the brain. And we call this chemical signaling neurotransmission. So you have neurons in your brain, and they all communicate by releasing little packets of neurotransmitters. And that's what my lab wants to measure and understand. How does your brain communicate using neurotransmitters? And so we know that this neurotransmission can change often during disease. So it's really important to study both the healthy brain to understand how it works normally. And then we use our techniques to study disease models to understand how neurotransmission might change during disease. My lab, for instance, studies model organisms, and so we become an expert in fruit fly neurochemistry. Believe it or not, the fruit fly has very similar neurotransmitters to what you and I have. It's very easy to do genetic models in the fruit fly. And so, for instance, our lab has taken a genetic model of Parkinson's disease, where we've inserted a gene that's known to cause Parkinson's disease, and then we've studied how that changes your dopamine neurotransmission. So we do a lot of studies on dopamine. It's a neurotransmitter that's important in locomotion and walking, and also in addiction and reward. So we can take our tiny little sensors and insert it into a tiny little fruit fly brain and then understand how dopamine is changing in Parkinson's mutations. Perhaps not surprisingly, what we found in this study is that the effect of having the Parkin gene that caused Parkinson's disease is worse in older flies than it is in younger flies. So again, this is a disease that often happens in aging. And so we see a lot more deficits in dopamine neurotransmission in aged flies with Parkinson's disease than in younger flies with Parkinson's disease.
So, Jill, lots of questions there. My first question is rather naive. How old is an old fruit fly?
They're not very old, which makes it a great project for graduate and undergraduate students. Yeah. It's just about 45 days. So the lifespan of a fruit fly is only about 60 days. So that's one of the reasons it's such a great model organism. We don't have to wait years for it to get old. It's just a couple months.
Is the idea then that you can also use the chemical sensors that you've produced in other organisms?
Yeah, that's the idea. So right now, our particular goal is usually to understand neurotransmitters in model systems. We're not particularly interested in going to humans. It would be an invasive technique that might not be well suited. But we do have some studies, for instance, in mice as well. So another fun study that we're doing right now is to look at the effects of focused ultrasound on your brain chemistry. So UVA has a lot of expertise in focused ultrasound, and this is a project that I'm working on with Wendy Lynch, who is a professor of psychiatry, and she and I were able to get both 3 Cavaliers funding and Brain Institute funding as a seed project that led to us getting an NIH grant then to study focused ultrasound as a possible treatment for addiction. So we are currently in rats. We're studying this in model organisms. But what we're doing is we're applying focused ultrasound. So this is really sound waves that go through your brain.
Right, so no blood, no scalpel.
No scalpel, because you can just sit the focused ultrasound on your intact scalp. So it's non-invasive. You don't have to do real brain surgery. And so you apply some sound waves, and we're applying them at a low frequency. So it's not going to cause any damage to your brain. Instead, what my lab is doing now is seeing how this changes the neurochemistry. And we've been able to work out parameters that will either increase the dopamine in your brain or decrease the dopamine in your brain if you use a completely different set of parameters.
And where are you focusing the ultrasound to generate these effects?
Right now, we're doing a circuit. So we are focusing the focused ultrasound on the prelimbic cortex. That's an area that's involved in reward and motivation. And then we're seeing how it changes dopamine in the nucleus accumbens, which is important for addiction. And so the idea is that we are hoping we can use these parameters, which our lab has worked out, and then my collaborator, Professor Lynch, is going to use these parameters to look and see how it changes behavior. And so the idea is to look at relapse. So, people have been taking drugs, they go off the drugs, they experience intense feelings of craving. And so our idea is if we can modulate the neurochemistry using this non-invasive focused ultrasound, we might be able then to reduce craving and help people stay off drugs.
Well, Jill, that's really great. There's so much happening there. But I also like to talk about the future. Time flies and the world advances at an incredible rate, certainly in the world of AI and a world awash in data. Tell us about the future of chemistry research. Maybe show and tell us about some potential applications that would affect us all.
Right. So I think that chemistry is really at the heart of many scientific innovations. So like we just talked about, my lab is trying to understand brain chemistry so that we can eventually regulate it and treat disease. And other labs are developing novel drugs for disease as well. And so while we've talked about a lot of fun applications of chemistry, I want to emphasize that at the heart, we are a basic science and a basic research department. And so basic science is really just understanding the world around us, making new molecules, understanding molecules in nature. And you never know where that's going to lead. You may invent a synthetic technique today, publish that in the literature, and somebody may pick that up and use that to make an amazing drug in the future. You may invent an analysis that you use for one thing today, but somebody may pick that up and use that for the latest COVID testing or whatever the next epidemic or disease of interest is in the future. And so I want to emphasize that while applications are super cool and important, that I think basic science also, just doing science to study molecules, is at the heart of everything we do. And that's going to lead, I think, to some amazing new applications. And you just never know kind of where the science is going to take you.
Yeah, thank you, Joe. That reminds me, when I was a graduate student many years ago, one of our friends, you might know her name was Nancy Goroff, and her advisor had just invented a molecule. I remember her telling me about this. And said, how do you invent a molecule? Haven't these things all happened somewhere in the universe before? She said, no. And they called it the buckyball. 3 months later, it's the rage. I'm learning about it on television. It's on the cover of Scientific American. And it was an example of a carbon compound that mathematically was, I guess, theoretically conceivable. It might be something that a theoretical mathematician might come up with, but turned out to be a major discovery in the real world. And I thought that was fascinating. So I'm glad that continues to this day. So, Jill, I want to talk about your career path. It's something that I'd like to talk about with everyone that's on the podcast. Can you tell us, when were you first drawn to chemistry? Was it high school, elementary school? Did you do experiments in the basement with your dog like I did?
Yeah, so I grew up in the Maryland suburbs of Washington, D.C., and so my dad was actually a chemistry professor.
Oh, so an apple doesn't fall far from the tree.
It does not. But he taught at a small college called Gallaudet University, which is the university for the deaf. And so my dad actually taught chemistry in sign language, which still blows my mind. I'm fluent in ASL, but I can't teach chemistry in ASL. And so I was around chemistry from my whole life. I feel I would go and visit my dad's lab sometimes in the summer, and I was just kind of interested in chemistry. And I got into a special competitive science and technology school called Eleanor Roosevelt High School in Greenbelt, Maryland. And then I was surrounded in high school by all these kids who were just amazing and interested in STEM. I loved AP chemistry, and we were required to do an independent research project at this science and technology school. And so I ended up working in a lab at the U.S. Department of Agriculture at something place called the Beltsville Agricultural Research Center. And in this lab, it was a chemistry lab, they made insect attractants. And so I wrote a high school thesis entitled Monofluorinated Analogs of Methyl Eugenol as Attractants for the Oriental Fruit Fly. You probably have no idea what that means, but I think it shows I was doing a high level of science in high school, right? And so I knew I wanted to study chemistry in college. I went on to the University of Delaware. They had an amazing honors program that allowed a lot of research experience. So I was able to study chemistry there and do some research. I began studying analytical chemistry there, studying mass spectrometry of DNA. And I also was able to do a research exchange program where I went over to London and went to Imperial College. And there I started to study biosensors, which is pretty much what I still study today. And so those experiences really shaped me, gave me great research experience early. I went on to study at the University of North Carolina at Chapel Hill for graduate work. And my advisor there really was in the heart of this field of doing analytical chemistry and neuroscience. And so I got into that field and I just absolutely fell in love. Did a postdoc with a psychologist doing behavior and neurochemistry at the University of Michigan. And then I came here to University of Virginia in 2005 and have worked my way up all the way from assistant professor to associate to professor to chair. I love it here, and I've really had a great time establishing my career here.
That's super exciting. The apple doesn't fall far from the tree. I get that. My father was a mathematician, and when I was a kid, different from your experience in the lab, but as a kid, my dad would sit me at a little table, and I'd have to do geometry problems in the summer while he did his big boy research. I actually didn't think that was very cool. So as department chair, I feel the need to talk about the undergraduate program. So as I understand it, UVA Chemistry has done a deep dive, thought very seriously about redesigning or updating the undergraduate curriculum. Tell us about that.
Yeah, so we've spent a lot of time really thinking about the success of all of our students in chemistry classes at the University of Virginia. And the chemistry faculty really have a heart for this. And so what we realized was that in some of our chemistry classes, underserved students and first-generation students didn't always do as well as more traditional background students. And so we had a team of faculty, including Professor Linda Columbus, Kevin Welch, Lisa Morkochuk, Marilyn Staines, and they worked with also some staff members at the College of Arts and Science to redesign our general chemistry curriculum. And so what we have now is just one lecture per week where we introduce material, and then one team-based active learning class per week where you work with a group of students to work through problems and get a deeper understanding of the material. And so this radical change has really improved student performance performance for all groups of students, but especially underserved students who now have a team to help them understand concepts. And so we've now really expanded this active learning to many of our different classes in the undergraduate curriculum.
So previously, if chemistry was taught here in a way that was similar to how I learned chemistry in college in the 1980s, it was boring lectures. 150 of us in a room, old professor actually smoking a pipe back then, Monday, Wednesdays, and Fridays, 8 to 8:50, and frightening exams a couple of times a semester. I want to take a chemistry class. It sounds like much more meaningful.
Right. The students are really now getting more engaged in their own learning, and that's what's so exciting. They're not just watching the professor do chemistry, they're able to do it themselves. And in that line, we've also redesigned some of our lab classes. You know, a traditional chemistry lab is like a cookbook. Mix this, mix that, get this result kind of thing.
And don't burn down the lab.
But it doesn't teach you that much. It doesn't allow you to really learn the scientific method of designing your own experiments. We've introduced more active learning experiments into the lab as well, allowing students the chance to design their own experiments. So I'll give you an example from the class that I teach. I teach the analytical chemistry lab. And if you walk in, it kind of looks like the labs that you see on those TV shows like CSI or NCIS. All those amazing instruments that just spit out answers on TV, they're not quite like that in real life. And so my students learn to use all of those instruments and analyze real life samples. And so at the end of the class, I give them real life samples like food or vitamins, alcohol, vanilla, that kind of thing. And I say, pick an instrument and go back and analyze it like you're the FDA. Tell me what's in the sample. Tell me if it's pure. Tell me about any contaminants that you see. And so they're learning real-life applications. I don't tell them a procedure. They have to figure it out themselves. And so with that, I think we're producing much better scientists and much better chemists by allowing them to practice the scientific method in these lab courses.
That sounds fun. For students and the members of the UVA community that are interested in chemistry, they're not already yet in the department, how can they learn more about the department and get involved, going beyond signing up for classes?
Right. So I think you could go to our department website to learn about our special events and seminars. And also we have some social media like LinkedIn that you can look at. But even more than that, if you're out in the community, you might actually be able to interact with our chemistry graduate student outreach group. That's called Chemistry Lead. And their mission is to bring chemistry to kids. And so they're out in the local schools, oftentimes local community fairs, the Discovery Museum, designing simple experiments to allow kids to get excited about chemistry.
So there you have it. This has been wonderful, Jill. Let's wrap up with maybe a fun, unrelated story, maybe a fun tidbit. What would you like to tell us?
Well, if I think about what I love here about Charlottesville, I have this real passion kind of for the outdoors. And we're blessed to live on a large property out in Ivy on the Meacham's River. And what's so cool about it is that there's so much wildlife. So just a few weeks ago, I was home with my daughter. She was sick from school, and she's like, Mommy, look, there's a bear on the porch. And there, rambling across the porch, is a bear who takes its time to enjoy our property with us. We're watching him out the window. You never know what you're going to see out there. And so when I'm not too busy doing tons of chemistry experiments in the lab or running my kids around to their sports and activities, I love to spend time outside. And Charlottesville is just such a great place to live and be.
Well, Jill, thank you very much. We're delighted to have you here at UVA leading the chemistry department. You're definitely fulfilling Jim Ryan's mission for UVA, his charge to be great and good in everything that we do. And I'm Ken Ono, STEM advisor to the provost and the Marvin Rosenblum professor of mathematics. And you've been listening to Who's in STEM.
Who's in STEM is a production of WTJU 91.1 FM and the Office of the Provost at the University of Virginia. Who's in STEM is produced by Catherine Kossaboom, Claire Curzon, Benjamin Larson, Mary Gardner-McGee, Katie Nichols, and Rhea Verma. Our music is composed and performed by Robert Schneider and John Ferguson of Apples in Stereo. Follow us on Facebook, Instagram, and Twitter. Listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the university.